back to the channel. Let's get right into this convolutional network problem. So this problem says that there is a network designed to classify 25 objects in an 80 by 80 RGB image, and then it specifies all the information about the layers. So what's important to note before we actually get into the problem is it asks us to keep the output spatial dimensions the same as the input spatial dimensions. So in this case, we're going to be using the equation that determines the output based on a kernel's size and the number of filters to calculate the padding to preserve the original dimensions instead of the other way around. Maybe you could get a problem that asks you to calculate the output size depending on a certain padding. But let's get right into it. So this first layer right here, it says layer 1, the first convolution. So let's write that down right here. And the input is going to be, it's always going to equal the output size. This is a universal truth on these problems. The input's always going to equal the output, but where do we begin? Well, it's an 80 by 80 image, and RGB means a depth of 3, right? Depth of 3. So let's write 80 by 80 by 3. That's our first set of dimensions. Okay, the kernel size right here is a 3 by 3 kernel. And you can either just put 3 by 3. I'm just gonna keep the information that the kernel depth needs to be the same as the input depth. You have to have compatible dimensions there. All right, so let's calculate the output size. Actually, like we talked about earlier, it's very simple. It's the same as the input, 80 by 80, but instead, since we're going to have 10 filters, we're going to have a depth of 10 on the output. The padding is where the equation comes in. Okay, so how do you calculate the padding? Well, the equation, let's go over the equation. It's going to be the floor of the input minus the filters size plus 2 times the padding over S, the stride, plus 1 equals the final output size. So let's reverse engineer this equation. We know that the input size is 80. So let me put this in a different color. I'm going to put this in blue. We know that the input size is 80. We know that the filter is a 3 by 3 filter. We're going to add 2 times the padding, which is what we're trying to find, and the stride is, we're going to assume the stride is 1. If the stride is not specified, assume a stride of 1. We're going to add 1, and the output is going to equal 80. All right, and we have this floor here, but I'm just going to remove those. How do we solve this? Okay, let's subtract 1 and multiply by 1. We're going to have 80 minus 3 plus 2 times the padding equals 79. And then let's calculate this. So 80 minus 3 is 77. We subtract 77 from both sides. 2 padding equals 2. The padding equals 1. Okay, that's a reasonable number. And now for the number of parameters and number of operations. Okay, so the number of parameters is going to equal here our kernel size times our output depth. Okay, so the kernel size times the output depth. So we're going to be using this kernel size, which accounts for the depth of the input. So we're just going to have 3 times 3 times 3 times 10. Okay, so that is that, and let me just draw an arrow here, have space. And then the number of operations is going to equal the kernel size times the output size. So that's going to just be 3 by 3 by 3, and we multiply it by 80 by 80 by 10. All right, let's carry on. So here, the next layer is the layer 1 second convolution. So continuing, obviously our input is going to equal our output, just like we said in the beginning. So 80 by 80 by 10. The kernel size here is another 3 by 3, but this time it has a depth of 10 because of the input. And then the output is going to be the same, 80 by 80. But we're going to have a depth of 5. All right, so the bottom line here is let's take a look at the information that we have above. So the number of filters here. If we try and calculate the padding again here, we're going to find, let's erase this work right here. And let's put the information in. So we have 80 minus, and then the filter is 3 plus 2 times the padding over 1 plus 1 equals 80. Look at that. Okay, so the padding is 1 again. It's the same equation. So let's just fill that here. It's the same exact equation. I'm going to delete this. And then the number of parameters and the number of operations, straightforward again. Let's just fill that out. So it's going to be the kernel size, 3 by 3 by 10, multiplied by 5, because that's the output depth. And then the number of operations is going to be 3 by 3 by 10, again, multiplied by 80 by 80 by 5, because that's the output size. Okay, so far so good. Pretty straightforward. Here's our first pooling layer. I'm gonna make it blue because it's a pooling layer, and pools are blue. The pooling layer, I'm gonna call it L1 pool, just like it says in the problem. The pooling layer is going to reduce the size of the input. This is a chance for the input size to be reduced. So right here, right, we're going to find that the input is the same as the output of the previous layer. So it's 80 by 80 by 5. And the kernel size actually doesn't really exist. You don't need to put anything for the kernel size here. If you want to put 2 by 2 because that's specifically the pooling filter, then you can, but it's not essential. But the output essentially, it's going to have the dimensions of the input, so it's just going to be 40 by 40 by 5 here. The padding, let's just put nothing there. And then the number of parameters, so you're just going to have no parameters, and then the number of operations, no operations. Okay. Moving on to the next layer. Oops, I should have put that in blue. The next layer is going to be the first convolution of the second layer. And as always, 40 by 40 by 5, as that is the output of the previous layer. The kernel size here is going to be a 3 by 3 kernel. Again, looks like we have 3 by 3 kernels throughout, so that's good to know. Okay, the output size, and it's going to be, again, the same as the input to preserve the spatial dimensions, except with oh, with a depth of 5, because there are 5 filters here. Okay, it happens to be the same. These are not the same number. This number comes from this 5, and then this 5 is going to come from here, right here. So let's do the padding again. We're going to find something important. It's going to be 40 minus 3 plus 2p over 1 plus 1 equals 40. Okay, 39. Let's just do some quick math. 37. 39. Okay, 37. Look at that. Again, we're going to get 2p equals 2, so padding equals 1. The padding is 1 again. So let's just fill that in. 1 for the padding. All right. The number of parameters is going to equal 3 times 3 times 5 multiplied by 5, because that is the output. And then let's just do 3 by 3 by 5 multiplied by 40 by 5. So far, this problem, it's pretty straightforward, right? Let me go ahead and fill out the rest of these rows really quickly so that we can get to the next different row, something that has a different operation. So all right, so here is another pooling layer. It's just like last time, 40 by 40 by 20, and then we're going to pool here the problem says 3 by 3 max pool to have the spatial dimensions. I'm just going to check something real quick. All right, I think this is a mistake. I'm pretty sure this is a mistake. I'm going to just correct this live here. 2 by 2 max pool. All right, to have the spatial dimensions. So here we have the spatial dimensions, so we're going to have an output of 20 by 20 by 20. And then let's fill the zeros in. All right, this is our first differing layer from the current norm. So here we're going to have two fully connected layers and a softmax layer. So I'm going to make these fully connected layers purple, and then I'll make the softmax dark blue. So let's go and say the third layer, let's say fully connected 1. Okay, so the input size, as always, is the same as the output of the previous layer. There is going to be no kernel size here. Instead, let's read. So we have 1,000 nodes each. So the output will be 1,000. And then the number of parameters is going to be 8,000, which is because of the 20. So we'll just write it out. 20 by 20 by 20 times 1,000. And then the same thing is going to be the case for the number of operations. Okay, well, right here we have the second fully connected layer, it's going to have 1,000 as the input. And before I continue, right, this fully connected layer is sort of finalizing. It's the end. It's unwrapping. Now, I could put not applicable here, and then the output will be 1,000. And here we could just put nothing for the padding. This is going to be 1,000 by 1,000. And then finally, we're going to have a softmax. I'm going to make this dark blue like I said. So softmax is going to have 1,000 as the input, not applicable for the kernel. And we have 25 classes, so we're going to have 25 outputs. All right. Nothing for the padding. And then 25 times 1,000 here and here for the number of operations and parameters and operations. Okay, in this case, it is not the kernel size is not applicable here, so we're doing the input by the output, right? This is how many operations and parameters we're going to have. So we have this table filled out.